Hi everyone, the topic of my presentation today is High DVDT Immune Fine-Controlled Parameter Adaptive Gate Driving Scheme for Synchronous Rectifiers SR in EV on-board charger. My name is Zhengda Zhang, a newly graduated PhD student from Arizona State University, and my advisor is Professor Qin Lei. First, let's do an overview of power electronics converters in EVs. This figure shows the structure of an EV. So basically, we have three power electronics converters in EVs. The first one is called the power electronics controller, which is also called a traction inverter. So the traction inverter is used to convert the DC power from the battery pack to drive the AC motor. So the two-level three-phase inverter is preferred because of the simple and robust topology and technology. This picture shows the commercial EV traction inverter from Tesla. The second power electronics converter is an EV onboard charger. So an EV onboard charger is used to convert the AC power from the AC outlet to charge the battery pack on the vehicle. So typically, a two-stage structure is preferred. The first stage is the PFC stage, which is used to do the power factor correction in order to meet the grid code. And the second stage is the isolated DC-DC stage, which is used to meet the safety regulations. This figure shows the commercial onboard charger. The third converter is the DC-DC converter. So a DC-DC converter is used to convert high voltage from the battery pack to give the power to the auxiliary devices in cars, such as audios and LEDs. Due to the high step-down ratio, a transformer is typically used. Meanwhile, the synchronous rectifiers is preferred instead of using diodes to improve the efficiency. This figure is the commercial DC-DC converter for an EV. The Department of Energy sets very aggressive power density targets by the year of 2025. For traction inverter, the target is set to be 100 kilowatts per liter. For onboard charger and DC-DC converters, the target is 4.6 kilowatts per liter. So we can see the major challenge in EV power electronics is the improvement of power density. The next question is how to improve the power density of the converter. The first approach is to improve the frequency of the converters. In that way, we can reduce the size for passive components. And the second approach is to improve the efficiency of the converters. In that way, we can reduce the size for heat sinks. And there are also other approaches, such as advanced packaging, which is not in the scope of this study. Next, let's look at a specific method to improve the power density, which is the synchronous rectification. The synchronous rectification is to replace diodes with actively controlled switches. So this is the topology of an LLC resonant converter. For the secondary side, a synchronous rectifier is preferred. The benefits of synchronous rectifiers are summarized here. We will have lower conduction loss, zero reverse recovery loss, and higher efficiency for the AC/DC stages. So we will have smaller heat sinks, so the power density is improved. The different turn-off scenarios for the SR are summarized here. So the first scenario is the zero current turn-off. So we can see the SR is turned off exactly at the current zero crossing. So this scenario is preferred. The second scenario is the early turn-off, so the SR is turned off prior to the current zero crossing. We will have additional conduction loss here. And last one is the delayed turn-off, so SR is turned off later than the current zero crossing, so we will have the circulating power. So prior to the turn-on of SR, we will have the body diode or the diode light conduction due to the SR delayed turn-on. So this period can be optimized because we can minimize the dead time. And if the SR is early turn on, we will have another high voltage drop, which is due to the early turn off. This should be solved because we need to detect the current zero crossing turn off moment for the SR. The major challenge for the synchronous rectification is the accurate and reliable detection of SR zero current crossing in very high frequency operation. Methods for SR zero current detection, ZCD. So the first method is to use the current transducer CT. The drawback of CT is the bulky and lossy at high frequency due to the magnetic core loss. The next method is to use a Rogowski coil. So Rogowski coil does not have a magnetic core, so the loss is reduced, but it is still bulky and high cost. And the next method is to use the commercial SR driver chip. This driver chip is from monolithic power systems. So the commercial SR driver is used to sense the device drain to source voltage. It basically uses the SR's RDS(on) as a shunt resistor. So we can see the package is very small. The commercial SR driver is extremely small, low loss, low cost, and no external current sensing components. So it is very suitable for high power density design. However, the commercial SR drivers have some drawbacks. The first problem is the significant early turn-off due to package swing inductance and poor noise immunity. So this figure shows the parasitic inductance inside the package. So due to the inevitable stray inductance, which makes the SR as an inductive branch rather than a pure resistor. Meanwhile, we know that for the SR driver, it needs a true threshold to achieve the driving scheme. So the turn-on voltage threshold is high, and the turn-off threshold is low, which is very close to 0. So the very low turn-off threshold makes the turn-off timing very sensitive to the noise. And because the sensor BDS is leading the current by a certain angle, so early turn-off will occur due to the parasitic inductance inside the package. The second problem is the controller side overvoltage and oscillation issues induced by the high DVDT switching transit. So this figure shows a equivalent circuit during the high DVDT transit. So during the high DVDT transit, for example, the battery voltage is 450 volt or even above. So this voltage is really high, and the junction capacitance of the blocking diode or the blocking FET will be in series with the input capacitance of the comparator or the SR driver chip. So because the voltage rating for this chip is very low, which is typically below 40 volt, so the overvoltage may occur. Meanwhile, the network capacitance will oscillate with string inductance. In that way, we may have overvoltage and oscillation issues for the comparator or the SR driver chip input. So this issue must be solved. The sensor VDS can be totally distorted. To address the first problem, adaptive SR on-time tuning method is employed. So basically, we do the low state detection within the turn-off period. We can set the turn-off period as half of the switching cycle. So we only have one threshold. Once the sensor drain to source voltage exceeds the threshold, we just do the on and off control so that we just increase SR on time by delta T. So we arrive at state B. At state B, we still have the sensor VDS voltage, which is exceeds the threshold. So we increase the SR on time by delta T again. And next, we achieve state C. At state C, we still have a small period which exceeds the threshold. So we increase SR on time by delta T again. At state D, we don't have the voltage, sensor VDS voltage, which exceeds the threshold. So we just decrease the SR on time by delta T. So eventually, the SR will switch between SC and state C and state D. So we will adaptively achieve almost zero current turn-off. The key benefits for these methods include the ZCD is adaptively achieved not by real-time measurement, so the impact from stray inductance is avoided. Second, only one high level threshold is used, so the noise immunity is significantly improved. So we do the experiments to verify the function of the adaptive on-time tuning. So we can see without SR on-time tuning, we have two low states. The first low state is due to delayed turn-on, and the second low state is due to early turn-off. With the SR on-time tuning function, we will have only one delay turn on load threshold. We don't have the second one. So the second one is due to the delay turn off, which is totally eliminated. To address the second problem, we proposed the novel BDS sensing circuit. So the basic idea is to employ a parallel switch, which is turned on when the main switch turned off. So in that way, we can clamp the output. Yeah, so in that way, we will avoid the overvoltage for the comparator or the SR driver chip input. And next, we want to do the self-driven. So we just use a different type of semiconductor to achieve the complementary logics. So in that way, we can use the same gate driving signal to drive all the switches. However, the drawback for this method is it can only sense the unidirectional BDS voltage because of the body dial. Next, we employ the bidirectional switch concept. We anti-series connected two switches, P MOSFETs. In that way, we can block and sense bidirectional BDS. This is our proposed BDS sensing circuit schematic. So we can see the key elements are Q1, Q2, and S1, the three auxiliary switches. It should be mentioned that here R4 is used to suppress the transient current in the Q1, R4, and Q2 branch when a large negative VDS occurs. The key benefits are summarized here. First, three auxiliary switches are self-driven by original SR gate driver. No extra signals and drivers are needed. Second, the auxiliary switches are low current, small package, and low cost, so we can achieve high power density. Third, the output voltage is safely clamped, so the overvoltage and oscillation issues are totally avoided. More explanations about the operating principles for the proposed VDS sensing circuit. So we can see the R3, D3, and C2, R3, D3, and C2. This network is used to turn on S1 later than the SR and turn off S1 earlier than SR to safely block the high voltage from the main switch side. Second, the R1 and C1. The R1 and C1, they are used to attenuate high frequency noise without introducing significant delay. Third, during the high DVT transient, the Q1, R4, and Q2 branch will bypass the displacement current and clamp the output voltage. So the equivalent circuit is shown here. So this branch provides low impedance bypassing path. In that way, the controller side overvoltage and oscillation issues are totally avoided. Next is the verification part. We use the proposed SR driving scheme in a 3.3 kilowatt CLLC converter. So this is our topology. So this is the structure for a two-stage EV onboard charger. The first stage is a PFC. The second stage is a CLLC resonant converter. So we utilize the variable dislink strategy to improve the system efficiency. So in that way, we can reduce the voltage regulation range for the CLLC. Although this may sacrifice the efficiency from the PFC a little bit, but the system efficiency is still significantly improved. So this is our prototype. It is modular designed, so we can see two 3.3 kilowatts CLLC resonant converter. They can be connected in series for the primary side and connected in parallel for the secondary side. The key parameters are summarized here. We use Infineon 600-volt GaN device. It should be mentioned that to compensate the double line frequency voltage ripple from the PFC DC link, we still need to do a little bit range of frequency regulation. Next is the prototype demonstration. This is our prototype of the modular designed 3.3 kilowatt CLLC resonant converter with a proposed VDS sensing circuit. So this is the primary side and this is secondary side. For both sides, we utilize Infineon GaN devices, which are under this heatsink. And this part is the planar transformer, which has very low profile. And under this planar transformer daughter board, we can see the resonant inductors and the resonant capacitors. And on the back of this motherboard,
we can see the gate driving circuits for the secondary side as well as for the primary side. So if we zoom in, we can see this part is the proposed drain to source voltage sensing circuit. So we can see how small the circuit is. In that way, we can achieve very high power density of this prototype. So the power density of this prototype achieves 130 watts per cubic inch, which is outstanding.
Next is the validation part. So we conducted a full load test at the resonant frequency. So we can see the sensed VDS voltage is very clean. And we can see a small short early turn off, which is introduced by the small filter, which is acceptable. And we can see we don't have any overvoltage and significant oscillations for the controller side. Next is the validation for the non-resonant frequency. Again, we can see the sensed VDS voltage is very clean and no significant oscillations. And still we will have a acceptable early turn off, which is due to the small filter. And we also measure the efficiency of the CLLC resonant converter. So we can see the proposed SR driving scheme improves the system efficiency by 1.23% compared with the commercial SR driver. And the average frequency is very high, efficiency is very high, is around 97%, and the peak efficiency is around 97.6%. So the state-of-art GaN-based 3.3 kilowatts LLC converter, the peak efficiency is 97.4%. However, their power density is not comparable to our work due to the low operating frequency. Thank you very much. That's all I have. For more information, please check out our article, High DVT Immune Fine Controlled Parameter Adaptive Synchronous Gate Driving for GaN-Based Secondary Rectifier in EV Onboard Charger in IEEE Journal of Emerging and Selected Topics in Power Electronics. Thanks again.